Welcome to the Electrical and Electronic Engineering Lecture Series. Your anchor person is Professor Michael Sindinechi, and our topic today is Module 028, Coding in Communication System. Please follow me in the engineering lecture series by subscribing to my YouTube channel at https://youtube.com/@ndidechimichaelc. Like, share, and drop your comments in the comment section or reach out to me using my email addresses. You can listen to my lectures on pulse code modulation. It's given in Module 022. Also, prelude to this lecture is the sampling theory, which is also given in Module 018. And of course, the other one, which is multiplexing technique, given in Module 026. In this lecture, I'll be bothering you with some self-tests to know how far and how well you've been understanding the lecture. It will be right if you answer those test questions, self-test questions in the comment section. I will go to the comment section, look at your answers, help to moderate and give you the correct answer. So we go. Coding in communication systems. The basic aim of any communication system is to provide error-free transmission of information from one point to the other. For analog transmission schemes, the amplitude of the signal reflects the information of the source. For digital systems, the analog information will first be translated into a stream of zeros and ones. For you to see how this transformation takes place, I refer you to my earlier lecture, as I said, the pulse code modulation. The main advantage of using digital system is that errors introduced by noise during the transmission can be detected and corrected. So that leads us to the self-test 1. This translation of analog information into streams of zeros and ones is called what? Coding in communication can be classified into 4 areas. The first one is data compression. By data compression, we mean to reduce space occupied by data stream. And we ask, in computer terminology, data compression is called what? Then we have the next, which is data translation. To change the form of representation of the information so that it can be transmitted over a communication channel. And the error control is to encode the signal so that errors can be detected and corrected. And the final one, which is encryption, is to encrypt information for security purposes. Three of these will be treated here as source and channel coding. So let's start with source coding. In source coding, the information to be transmitted is first translated into a stream of bits, that is zeros and ones, and compressed to remove redundancies. See the earlier lecture on sampling. This process is called source coding. There are many ways to achieve this. One way is to use known codes like the ASCII codes. ASCII stands for American Standard Code for Information Interchange, or the one called the EBCDIC, which is Extended Binary Coded Decimal Interchange Code. Now, these two codes are fixed length code words. For any letter, you have a fixed number of bits to represent that letter. That is what we mean by fixed length code word. Let's take example. If the word woman is to be transmitted using the ASCII code, which is a 7-bit code word, it will be coded as 101011 to represent W, 1001111 to represent O, 1001101 to represent M, 1000001 to represent A, and 1001110 to represent N. So you see that if you use an ASCII code to transmit the word woman, you will need 7 times 5 bits, which is 35 bits, to transmit it using the ASCII character. However, this word woman can be transmitted using lesser number of bits by making an assumption. It is a known fact that the occurrence of W, at least in the English lettering, which we are using, is not as often used as that of O and A. So if there is a way of encoding information such that alphabets with higher probability of occurrence are assigned with shorter code words, while those with lower probability of occurrence are assigned with longer code words. Then, in overall, it will be possible to conserve the number of bits to be sent to the channel while sending the same information. Okay. This can be achieved by the use of variable code word. So, one example of a coding technique that allows this variable length code word is the Huffman code. Huffman coding technique is best illustrated using an example. So let's use the example woman, we have considered that if we are using ASCII, it will take us 35 bits to transmit. So when we use this woman, we assign the letters certain levels of probability of occurrence. For instance, in this English lettering or alphabet, it is likely that O and A will occur more often than W. So we assign the ones that occur more often higher probability of occurrence, so that we use fewer letters to fewer bits to represent them. But note that the sum total of their probabilities must be equal to unity. These are basic things we learned in our basic mathematics. So say, take for instance the word under consideration, woman. We know that letters A and O are more likely to occur than W, M, and N if we are going to continue to make sentences using the English alphabet. So we can assign arbitrarily probabilities of occurrence. Take for instance, we say that A is more likely to occur if we are writing some, words in English language. So we assign probability of occurrence A equals 0.5, and probability of occurrence for O equals 0.25. Probability of occurrence for M equals 0.125. Probability of occurrence for N equals 0.065. And probability of occurrence for W equals 0.06. Like we said, these probabilities are assigned arbitrarily, but the important thing is that their sum must be equal to unity. It doesn't matter how you assign them. You are the designer, so you assign what you like. But if you go ahead to assign the words that are less likely to occur higher probabilities, you will end up using more bits than required. So after assigning the probabilities of occurrence, we order the alphabets in decreasing probability and denote them as L1 to Ln. In this our case, N is equal to 5 because there are 5 letters in the word woman. So we combine 2 letters, Ln, that is L5, Ln minus 1, that is L4, having the lowest probabilities. We assign 0 to the last letter, which is Ln, and 1 to the second to the last, which is Ln minus 1, in which case is 0 to L5 and 1 to L n minus 1, which is 4. We form a new source alphabet of n minus 1 letters by combining L minus 1 and Ln into a new letter L minus 1 with probability P minus 1 equals Pn minus 1 plus P. We continue to repeat this process until the final source letter has only one symbol with probability equal to 1. Let's see an illustration. See, we said the word woman. We assign probability A to have probability of occurrence 0.5, O to have probability of occurrence 0.25, M 0.125, N 0.065, W 0.060. So from our earlier description, we say that we put them in decreasing order of probability. So you see 0.5 is higher than 2.5, 0.25. 0.25 is higher than 0.125. 0.125 is higher than 0.065. And 0.065 is higher than 0.060. Now, when you put the last two, which is 0.065 and 0.060. You combine two of them, you see we used green line to combine two of them. If you sum them, it will give you 0.125. Now, we said the lowest one, which is Ln, we assign 0. The next one, which is Ln minus 1, we assign 1. So you see that W is the L5, N is the L4. So we assign 1 there and 0 down. Now, we combine the next one. So this time around, you see Wn sum up to 0.125. So 0.125 becomes the next Ln, while that M becomes the next Ln minus 1. So you sum them, we represent the two with yellow line. If you sum the two, it gives you 0.250. The down one, which is the one that is Ln now, gets a 0. Then the upper one gets a 1. So that's 0.250 becomes the next Ln, and 0 and O, letter O, becomes the next Ln minus 1. We represent them by red. So when we represent them by red, we sum them to give us 0.500. You see that becomes the next Ln. We represented it with purple line. So you now add it with the letter A. It gives you the next total, which sum up to 1, which is the final sum. So you also label 0, 1. Now, what do? You now see that from W to that last point, you have 1, where the probability summed up to be 1. You see that W will be represented by 0, 0, 0, 0. That is, you go through the branches and pick what is there until you get to that point. Now, N, we go through 1, then 0, 0, 0. While M, we go through 1, 0, 0. And O, we go through 1, 0. And A, we go only through 1. Now, it doesn't matter how you put them, but the important thing is that we have seen that we are using 4 bits to represent W, and we are using 4 bits to represent the next one. We are using 2 bits for the other, 3 bits for the other, 2 bits for the other, and 1 bit for the other. Meaning that if you total it, it gives you 14 bits. So you see that when we use Huffman coding, we have succeeded in bringing down the number of bits. Remember, when we use ASCII, we transmitted 35 bits to represent woman. Now, we use Huffman coding. We are transmitting only 14 bits. And we say that this has translated to 60% savings in the bandwidth. So note that in practice, all the possible characters to be used in transmission are assigned frequency of occurrence. Note, most of the time, ASCII codes are written in hexadecimal. When we treated computer number basis, we saw how that conversion is being done. So this leads us to self-test 3. Say, give the ASCII binary equivalent of transmitting the letter help. Like we said, ASCII is a fixed length code word. So H will have its own 7 bits, E will have its own 7 bits, L will have its own 7 bits, and P will have its own 7 bits. So you have to transmit that to do that. So your work here is to look out for the ASCII table and find the binary equivalent of H, binary equivalent of E, binary equivalent of L, and binary equivalent of P. Then you give its hexadecimal equivalent. When you have put that binary numbers, which is 7 times 4, 28, then you code it back in decimal. That will show us if you really understand, our past lectures on computer number systems. But if you look at, what we have done, it looks so simple. There could be a time this tree we plotted will be so complicated that when you add the last two or the least two probabilities, it will be bigger than the next one. So you will have to continue to reorder. If you try to follow this pattern we have used, you may never get it correct because there will be multiplicity of lines crossing one another. So I will dedicate the next lecture to just solving an example of Hoffman coding that has complicated probabilities or frequency of occurrence. You will see how you will now do that, and it will form a very big tree, like when you have, hierarchical order of things. So we will do that by next week. It will just take us about not up to 20 minutes. But I would like you to join to see the use of Hoffman coding to solving real life problems. This one we did, we tactically fix the probabilities so that the lines do not cross one another and it will not be complicated. So now, remember we talked about source coding. And one thing we said about source coding is that you remove redundancies so that you can conserve space, which in computer terminology we call zipping. You say, this is a zip file. It helps you to reduce the file, the volume or the size of the file. At the receiving end, the file is unzipped. So that zipping is the source coding that made it to be that. So channel coding. Channel coding is also known as error control coding. And it is a method employed to detect and possibly correct errors that occur in the transmission medium. It is done by introducing redundancy to the stream of bits to be sent to the channel for transmission. The channel encoder will add bits to the message bits to be transmitted systematically. After passing through the channel decoder will detect and correct the errors. What are we saying? In channel coding, you introduce redundant bits. These redundant bits helps to detect errors that occur in the transmission channel. Of course, we have met transmission channels like microwave links, optical fibers, microwave, satellite communications. The link that help you to communicate from one point to other has so many interferences, absorption, distortion, degradation. So all this affects the bits you transmit. So we are saying to be able to decode at the receiving end whether there is error with this signal transmitted, we have to introduce some redundant bits. Take for example, we want to transmit 0, just one bit, 0. If we transmit that one bit 0, and due to noise, it turns to 1, how do we detect that what was transmitted was 0 instead of 1? So instead of us to transmit just 1 0, we can transmit 2 zeros. Transmitting 2 zeros does not change it from not being 0. We can also transmit 3 zeros. Transmitting 3 zeros does not mean that it is no longer 0. We can also transmit 4, and so on. So by transmitting 2 zeros instead of 1, instead of 1 0, we have introduced a redundant 0. That is what we mean by introducing redundancy. Instead of transmitting 1 0 or 2 0, we transmit 3 zeros. By transmitting 3 zeros, we have also introduced 2 redundant bits or 2 redundant zeros. If we do that, transmit 4 zeros instead of 1 0, the meaning is that we have introduced 3 other redundant bits. So we say, instead of transmitting only 1 0 through the channel, due to the presence of noise in the channel, the received bits may become 01 or 001 or 01 or 0010. But since either 00 or 000 or 0000 could have been sent by majority logic decoding scheme, this is a scheme, so we'll go into it much later, it will be decoded as 00 or 000 or 0000, and therefore the message has been a 0. This would not have been possible if only 1 0 had been transmitted. In the presence of noise, it may have changed to a 1 bit, and it will be difficult to interpret it as otherwise. So examples of channel encoding schemes include the block codes and the convolutional codes. If you subscribe to my channel, in our later lectures, we will continue to look at all this, and probably we will get, you will follow us at the point we will be treating block codes and convolutional codes. Now, we get to the next topic, which is principles of error control codes. So, the type of channel employed in a given transmission system plays an important role in determining the kind of coding to be employed. For instance, if a two-way communication link with possibility of requesting for a retransmission is being operated, one can restrict himself to only error detection. But if the link is a one-way and the retransmission cannot be called for. Then codes which detect and correct errors must be employed. I want you to get it well. If a two-way link with possibility of requesting for a retransmission is being operated, one can restrict himself to error detecting only. If you detect the error, you don't bother to know what it is. You send message back to the transmitter that there is error, retransmit, what you may call negative acknowledgement. If the link is a one way and the transmission cannot be called for, then codes which detect errors must be employed. All methods of obtaining error control require addition of extra digits to the binary code word. And want to task our brain again, which we say self-test 5, to give an example each of what you know as a two-way and a one-way communication link. Please just think about it. Which communication do you think is a two-way that if there is error, you can call back for a transmission, and if there is error, you will not call back, your system should be able to correct the error. So, say these digits are used in some way to check validity of the received informational digits and are referred to as parity digits. Remember what you said, that you add a bit, that bit you are adding is called the parity bit. And this parity bit helps to check the validity of the received informational digits. They themselves, that is the parity digits, do not carry any information, but its presence indicates whether the informational digit arrived in error. So we say they are generated from the information digits by some suitable logical manipulations. The simplest parity check involves a count of the number of ones in the information part of the code word. If this count is even, a 1 is inserted as the parity check digit. If it is odd, then a 0 is inserted instead. For instance, if we are to transmit an arbitrary number, say 19, 27, and 20, we will transmit for 19, we convert it to its binary equivalent, which will give us 10011 as the information. That is 19 we want to transmit. So this 1011 is the information bit. Now, we count the number of ones in that information bit. If you look at it, it's 3, which is an odd number of ones. So we insert 0, and that will give us 100110. That last 0, which we put in red, shows that that is not part of the information. It's not part of the 19, but it is helping us to show that the number of one bit in the information is an odd number. That will help us so that if the information is received in error, that is, if the information bits arrive in error, we'll be able to detect, as we will see very soon. Now, the next one is 27. If we convert 27 to its binary equivalent to get it in bits, it will give us 11011 as the information bit. And if you count the number of bits, one bit there, it is 4, which is even. So we insert a 1 as parity bit, which gives us now 11011. We append that parity bit, which is 1, in red. Likewise, 20, we do the same thing. 20 has 2 ones, which is even. So we add a 1. We say, therefore, the sequence to be transmitted will be 10011. You see the red 0 showing the parity for that. 11011, you see the 1 in red, which is the parity, and 10100, then you see the 1 which in red, which is the parity. So we say, note that every sixth bit in this sequence is the parity bit. That is why we try to, use red to show the parity bit. Now, suppose the first word there, which is 19, is received in error as 10. Look at the error. We use tick 1, or we made the 1 to be different. It's received as 10110. Sorry, 101110. Remember, the first 5 digits is the information representing 19, which we see as 10011. But while this transmission is taking place, an error occurred in the third bit. We say the parity checker at the receiver will count an even number of ones. You can look at it, the number of ones are now even. And generate a 1 as the parity digit. Since they received and the locally generated parity differs, an error will be registered. We take that. 19 is 10011. Because we have odd number of ones, it appended 0 and transmitted 100110. But along the channel, something happened. An error occurred in the third bit. So what the receiver is seeing now is 101110. Now, the receiver will receive it, generate its own parity bit. While generating its own parity bit, it will see 4 ones, which is even number, it will generate parity bit 1. When it compares it with what is receiving, we will see that there is an error automatically, because what is receiving is supposed to have odd number of bits, but what it is seeing is even number of bits. So automatically an error is registered. Now, so this kind of parity check can only detect the presence of an odd number of errors. It becomes an impediment. So it has limitations. But then let's go on and see how it detects this error that is occurring in the third bit. An even number of errors produces self-canceling parity check situation. Hence, a code based on this principle is suitable only for independent errors. Also, since the code is only capable of error detection and has no inbuilt error correction, it can only be used for two-way communication length. It can only detect error. It cannot correct the error. So it will be only suitable for two-way, so that if it detects the error, it will ask the transmitter to retransmit. Then we continue by looking at block coding and decoding. The concept of parity checks were introduced in the section above. In this section, we shall concern ourselves with the type of codes known as systematic codes. A systematic code is one in which the information digits appear unchanged within the code word. Thus, we will have something like this: I naught, I1, we continue to I k minus 1. Why are we having ik minus 1? Because we started with 0. So the last I must be whatever number there minus 1. And we have that I represents the information bit. For instance, in what we have considered, 19 is the information bit, while the parity we introduce is the control code. I'm saying when you take this pattern, I naught to ik minus 1, c naught to cj minus 1, we call it a systemic code. You say where I naught, I1, ik minus 1 is called the k information digits in the code word, while c naught, c1 to cj minus 1 is equal to the j parity check digits in the code word. The parity check in the code word may be formed in one of the four ways. A check digit required to provide a parity check on any given set of information digits may be chosen so that the number of binary ones in the information digit sequence is even. The binary ones in the information digit sequence is odd. The binary zeros in the information digit sequence is even, or the binary zeros in the information digit sequence is odd. Let us explain what we mean here. We said, under normal circumstance, when the uh, binary ones in the information is even, you insert a 1. When it is odd, you insert a 0. But if I'm doing my own design, I can decide not to use that standard parity check pattern. I can decide to tell you that you insert a parity bit, which is 1, if the binary ones in the information is even, which is the normal thing. But I can decide to say you insert the 1 if the binary digit is odd. So you see, when I do that, I have deviated from the standard known by everybody. So only my systems will understand that while other systems look out for even number of ones to insert one parity bit, my own system will be looking out for odd number of ones. Likewise, when the normal system will be looking for odd number of ones to insert 0, my system will be looking for even number of zeros of ones to insert 0. So it is a design that when you do, you specify what you want and your system works like that. But the one we said even insert 1, odd insert 0 is a standard rule of thumb for parity checking. Now, let's take a quick look of how this your system pinpoints an error and corrects it. Say, an error correction scheme known as iterated coding allows us to extend the simple parity check technique. For example, let's consider an array of 3-digit code words given as I0, I1, I2. So the first one transmits 010. The second one the second number to be transmitted is 111, and the third one is 101. I repeat, you have a number having 3 bits, and there are 3 numbers. You want to transmit them. So you transmit the first one, 010. You transmit the second one, 111. You transmit the third one, 101. Now, if we use the normal parity check, the first one is having an odd number, so it should have parity 0. The second one is also having odd number, that is 3 ones. It will have parity also 0, while the third one is having even number. It should have even, parity 1. So let's look at it. We then perform parity checks on both rows and columns with an odd check on the binary ones. You can see I deliberately put odd check in red to show that we are not using the normal parity checking, which is even check. That is why I try to show that, requirement that it is odd check. So if you look at the first bit transmitted, which is 010, if we use the normal parity checking, it is an odd number of ones. So our parity should have been 0, but we changed it and said we are using odd check. So when we are using odd check, it means that for that first information transmitted, which is 010, the binary number, the binary one in that number is 1, is odd. So we put a 1 on the right as the parity bit. If you look at the second one, which is also 111, instead of having a 0 under normal circumstance, we also put it 1 because we are using odd check. And the third one, which is 101, instead of having the parity bit 1, because we are using odd check, we put a 0. I hope this is well understood. Now, we separate the parity bit from the information bit. So, what do? We look at the vertical check. 011, we have even number of ones. Instead of inserting a 1, we insert a 0 because we are using odd check. So the vertical, the second column, still 110, so we insert a 0. And the third column is 011, so the parity check also 0. Then we do the horizontal check. The first one, of course, we put the parity 1. The second one, so if we check the parity bits again vertically, it will also give us 0. So you see that the vertical checks, the horizontal checks, and the check on checks corresponded to 0. If you look at the last 000, that is row 4, the parity check there should be 0. If you look at it from vertical, the horizontal, that is column 4, it will give 0. So it shows that there is no error occurring in this transmission. Now, because the check on checks corresponds to what it should be. Now, instead of transmitting the sequence 010, 111, and 101, we add the parity bit. So we transmit 010 parity bit, 111 parity bit, 101 parity bit, then 000 parity bit. That is from the table we see before. So you see that we are transmitting four bits. The information is 9 bits, but we are transmitting how many bits now? Four. We are transmitting 16 bits. You can see what we mean by adding redundant bits. The real information is 9 bits, but what we are transmitting is 16 bits. The difference, which is 7 bits, is helping us for error detection and correction. So now, how do we detect those errors? How will that 7 extra bits help us to detect error? We see shortly. So we say with this, any error in code word in the array can not only be detected, its position within the code word can also be found and hence corrected. Take, for example, an error in the first code word, say 01, see the tick 1. Remember, the information word in the first one is 010. But now, what is transmitted is 010, and the parity bit is 1 because we are using object. But what the receiver is seeing, because an error has occurred in the transmission line, is 0110. I want you to get it very well. What we transmitted is, for the first number, is 010. The parity bit is 1. So we transmitted 0101. Now, at the receiving end, an error occurred in the third bit. So what the receiver is seeing is 011. But it sees it back and looks at it and finds that it's not supposed to be, because it's using odd check, but it's receiving even number of bits. And the parity shows that what is transmitted is odd number, while it is seeing even number. So you will do a simple computation to see where the error is coming from. So now, look at the first column, 01, the error occurred where we put red. So it will look at it using the odd check. The parity is 0. It marks it. That's why we marked it in purple. Then the second one, the parity is correct. The third one, the parity is correct. So now, like before, it does vertical check on column 1, does vertical check on column 2, vertical check on column 3, then vertical check on column 4. Then we will see that the check on checks is not correct. It's not corresponding, because that vertical checks, the parity will have been a 0, and the first one there, the parity will have been a 0. So it now looks at the coordinate where that error is occurring. If you look at the vertical checks, it's in column 3. If you look at the horizontal checks, is in column 1. So at the coordinates where they cross, it shows where the error is occurring. So it has not only detected the error, because it's binary digits, zeros and ones. So if that error is occurring on that point and what is there is 1, automatically the system on itself will change that range 1 to 0. The way it does that is being able to do error detection and correction. It doesn't have to ask any person to know that the error is occurring there, and because it is 1, it will just change it to 0 to continue. So say the underlying checks do not agree with those received, and they provide coordinates which pinpoints the incorrect digit. The error can therefore be corrected. If 2 digits are in error, it can still be deduced, but the errors cannot be corrected. You can see again another limitation. So we say, example, if the first code word had 2 errors, as shown, the computed parity checks, which indicate that 2 errors occurred, will indicate that 2 errors must have occurred. You can see it again if you do that checks, but then it will not be able to correct it. Now, there is a system that can now help to know where the error is occurring without you going through that analysis. And that technique is the Hamming code. You must have heard of it. So one of the early formal coding procedures was devised by R.W. Hamming. The general format is as shown for 4 information digits. You see C0, C1, I0, C2, I1, I2, I3. For the Hamming code, it is important you know this sequence. C0, C1, I0, C2, I1, I2, I3. The digits I0, I1, I2, I3 are the information digits, while C0, C1, C2 are the parity check digits. The check digits for this 7-digit Hamming code can be determined from the 4 information digits as follows. C0 is I0 modulo 2 arithmetic, I1 modulo 2 arithmetic, I3. And C1 is I0, I2, I3, and C2 is I1, I2, I3. Now, remember, I0 to I3 is the information digit, the information you want to transmit in binary. Then you generate by yourself 3 control parity checks. And this is the formula for generating the 3 control digits. Say the C0 is equal to this. Now, this sign plus circled in mathematics is called modulo 2 arithmetic. Modulo 2 arithmetic. And we want to see, how far you've gone in your digital logic technique, and we say, which logic gate performs this or equivalent of this modulo arithmetic in digital systems? which logic gate performs this module 2 arithmetic in your digital system? Please give us your answer in the comment section. I will get into the comment section and help you to sort it out. See people that will get it. So note that the parity check digits are generated from the information digits. You say, for example, if we have this I0 to I3 to be equal to 1101, it means that C naught will be I naught plus or modulo 2 I1 plus modulo 2 I3. If you put that, I naught is 1, I1 is 1, I3 is 1. So if you do that, it gives you that C yes is 1. Then the C1, if you put that, it gives you 1, 0, 1, 0. C3, C2 will be also, if you do that modulo 2 arithmetic, gives you 0. We say this gives that your control parity, which you have generated based on the information bit given to you, is 100. So if you now put this your code, you see that what you will have will be 1010101. That is C0 C1, I0 C2, I1 I2 I3. We give you that. So say suppose now that the code word was received with an error in information digit I1. If you look at that from the right, information digit I1 will be, the third from the right. So you will have 1010. Instead of 101, you have 001. So say we can recompute that parity check, which will now give us C0 0, C1 0, and C2 1. If we compare the two, so comparison shows a difference between received and recomputed parity check digits. That in C0 there is a change, in C2 there is no change, in C1 there is no change, and in C2 there is a change. So if we regard change as being equivalent to binary number 1 and no change as being equivalent to binary number 0, we can determine the position of the error within the code word by means of binary to decimal conversion. So we say C0 change, which we say 1, is 1 times 2 raised to power 2. C1 no change, which you say 0, is equal to 0 times 2 raised to power 1. And C2, which is 1 change, is equal to 1 times 2 raised to power 0. If you do that, it gives you 5. Automatically, it means that the error is therefore in digit 5, which is equivalent to I1. And these digits need only to be reversed for the error to be corrected. So you see, this one, it doesn't matter the number of errors occurring, you can, detect the point and reverse it. So the other digit positions are similarly covered by unique parity difference patterns as shown in table 1. So if you get your control digits C0, C1, C2. It will, if you recompute the parity and it gives you any of this table, automatically you know where the error is occurring. So you don't need to even do anything. That this C0, C1, C2 is just like a table of eight, if you draw a true table. So when it is 000, it means no error occurred. But if you recompute and get 001, it means that error automatically occurred in control C0. If you get 010, it means in C1. If you get 011, it means like what we have, which is 100, automatically shows that it is okay. 101 automatically shows that it is digit 5, which is I1. So it's as simple as that. So thank you for listening. Probably our lecture took too long. I will try to reduce the maybe call them. But I must say that opportunities are time conscious. If you waste your time, the train carrying them will pass. Therefore, always be time conscious to meet your opportunities. Thank you for listening.